Hi, welcome everybody. I'm Jacopo. I'm going to talk about a new way to probe features in the primordial power spectrum by looking at the stochastic background of gravitational waves. So, hopefully, with experiment like LISA. Before telling you what primordial features are, let me stress that people have looked for them in CMB and large-scale structure data for decades. And the reason is that features carry important information about the physics of the early universe. And finding traces of them would really mean open us a privileged window on the physics at energy scale that we'll never be able to reach on Earth. Let's consider, for instance, inflation. Inflation is the best paradigm of the early universe we have nowadays. And what inflation, the beauty of inflation is that it provides for us the boundary conditions for the subsequent cosmological evolutions. So really, more precisely, the correlation of the scalar fluctuations generated during inflation leave their imprints in late time observables, such as the temperature anisotropies or the distribution of galaxies at large scale. And by looking at the CMB, what we learn is that these perturbations are almost Gaussian, almost scale invariant, and their power spectrums, the two-point correlation function, is basically parameterized by two parameters, their amplitude and the scalar tilt, which are 2 out of the 7 parameter cosmological parameters. This almost scale invariant power spectrum is in perfect agreement with the simplest inflationary scenarios, and people have looked obviously at departure from that. So here, just to give you an idea of the energy scales and how these two parameters probe ratio of energy scale during inflation. The typical energy scale can go up to 10 to the 14 GeV, so 10 order of magnitudes above the energy reached in present colliders. Now, as I was saying, people have looked from departure from the standard scenarios, mainly because there is now this tendencies of thinking about inflation as a gigantic cosmological colliders. And so, for instance, certain configurations, this is a famous result that tell us that certain configuration of the three-point function would carry information about the mass and the spin of the particle present at those energy scales. And the departures from the standard scenarios are departures from the scale invariance in the primordial power spectrum. So there are many phenomena that could give rise to them, but the outcome are quite generic and are in the form of what are called primordial features, which are oscillations in the primordial power spectrum. So here you see two examples, the two characteristic examples, so oscillations which are periodic in momentum space or log periodic in momentum space. So these are the type of features motivated by high energy physics that people have looked in data. And the reason is that this type of oscillation can probe new mass scales, new coupling, and the pattern can even test the inflationary paradigm itself. So as I was saying, people have looked for these features where the primordial power spectrum is constrained, so where we have data, CMB and large-scale structure here. What we have in mind is a departure from the scale invariance at smaller scale, which correspond to a period of the inflationary history which are completely unconstrained by data. And the cartoon here shows a peak in the primordial power spectrum, so a huge departure from scale invariance, which is motivated by trying to explain with inflation all dark matter, basically in the form of primordial black holes. A peak like this is now a standard law. A peak like that would provide a mechanism to generate primordial black holes from inflation. Now, if the phenomenon triggering this enhancement lasts short enough, and by short enough I mean that, so this is the ratio between the energy scale triggering this enhancement and the Hubble scales during inflation, then what we show is that on top of this peak power spectrum, we have order 1 characteristics oscillations. Okay, so this is the type of feature we are looking for, features of small scales of this type. So what we are really looking for is like, to use an analogy, an itch-up in the womb. So basically, on top of an exponential expansion, you have at some point an hit, which leads to periodic modulations of the signal. Now, these are some results, a list of results, if you want, of the energy density of the stochastic gravitational wave background as resulting from features in the primordial power spectrum. On top you see sharp features, which I remind you are oscillation linear in the primordial power spectrum, which lead to this type. This is the simplest signal you can get. So on top of the peak, the characteristic peak that you usually have in the stochastic gravitational wave background from a peak in the primordial power spectrum, we have characteristic oscillations. Here are two examples. Sharp features, also the mechanism triggering the sharp feature, also lead to another patterns of oscillations, which has this shape, which order 1 oscillation directly in the stochastic gravitational wave background. And on the bottom panel you see the result from a resonant feature, so oscillations which are log periodic in momentum space, which could lead to a complicated pattern or a double peak pattern in the stochastic gravitational wave background. So let me advertise in this slide that after our first proposal, people have constructed many explicit models that can lead to features in the primordial power spectrum, in the stochastic gravitational wave background. Now, just to give you an example of what this oscillation in the simplest example of sharp feature could tell us. So here you see on top again these small oscillations in the stochastic gravitational wave background, which here are magnified by showing them as the ratio with the envelope. They can be fitted by a simple template like that, and what we learn from that is really the energy scale at which the phenomenon triggering this enhancement in the stochastic gravitational wave background happens during inflation, when and for how long it happens during inflation. And by looking at the amplitude of this oscillation, we could really even probe the cosmic expansion history when these modes re-enter the horizon after inflation, so whether they were during radiation domination or some more exotic scenarios. This has been explained in this paper. Now, the question we ask ourselves is, okay, we would be able to reconstruct this type of oscillation, this type of features, if they were present in a stochastic gravitational wave background of cosmological origin. So we did first what I call an homemade search analysis. So first by an optimistic Fisher forecast that tells us basically that oscillation can be reconstructed at 10% if the overall amplitude of the stochastic background is above this value. And then using this algorithm, also a way to visualize a principal component analysis reconstruction to see if we can reconstruct when and what is the amplitude to reconstruct this type of oscillations. What we are doing now is within a wider project with the cosmological working group to look more in detail if we can reconstruct features with LISA. So the goal of this wider project, let me advertise it a bit, is first to build a template bank for the stochastic gravitational wave background signals coming from inflation. So this feature signal is one of them. Then doing the agnostic search with the binary algorithm, which was proposed by the cosmological working group in this paper, and which means really, you see here two signals for a peak, for a stochastic gravitational background coming from a peak power spectrum, and the one with the same envelope but with the features on top. And basically what this algorithm does is to separate in frequency bin the frequency space that LISA is sensitive to, and fit in each frequency bin in a clever way with a power loaded signals. And what we did, apart from this agnostic search, is really point 3 and 4, is to do a Fisher forecast by scanning of over the parameter space for each template. And for the parameters that are, let's say, borderline, we even do a Monte Carlo sampling to reconstruct the signal. So let me explain these 2 points here in a slide. So here is the 2D plot, where you have one parameter is the amplitude of the linear oscillation for this type of signals, and on the x-axis you have the amplitude of the overall amplitude of the stochastic gravitational wave background, and in colors you have the error on the amplitude of the linear oscillation. And then you see here for few points like this one in this box, you have the Monte Carlo sampling reconstruction here. Okay, so let me conclude. With fact, the stochastic background open a new window to probe inflation at small scale, and there is a huge amount of information hidden behind the possible discovery. And I will leave you here prospects and speculations to think about. So thanks a lot for listening, and don't hesitate to contact me if you have any questions.